The United States Department of Labor has proposed a rule regarding electrical standards, specifically, Electrical Standard Proposed Rule. This proposed rule was published in the Federal Register on May 3, 2023. The core purpose of this proposed rule is to update the Department of Labor's Occupational Safety and Health Administration, otherwise known as OSHA, regulations pertaining to electrical installations and equipment. An equally important aspect of the proposed rule is the establishment of new requirements designed to bolster electrical safety within workplaces. The public has the opportunity to provide feedback, as the proposed rule remains open for public comment until July 3, 2023. OSHA has committed to reviewing and considering all comments received before making a final decision on the rule. If the proposed rule is ultimately finalized, it is slated to go into effect 60 days after its official publication in a Federal Register. It is important to clarify a key point. The proposed rule does not establish a national electrical licensing system. However, the proposed rule does include provisions that would permit individual states to adopt their own electrical licensing requirements. Therefore, while it doesn't create a national system, it opens the door for states to implement their own licensing frameworks. Understanding the impact of electrical safety regulations, particularly those enforced by OSHA, is critical for anyone working with or around electrical systems. These regulations are designed to minimize the risk of electrical hazards, which can lead to serious injuries or fatalities. Let's delve into some specific areas typically covered by such regulations. Firstly, wiring methods and materials. OSHA regulations specify acceptable wiring methods and materials for different applications. For example, the type of cable used, such as non-metallic sheet cable, armored cable, or conduit, depends on the environment and the potential for physical damage or exposure to moisture. Secondly, overcurrent protection. This is a critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect circuits from excessive current, which could cause overheating and fires. Regulations dictate the proper sizing and installation of these devices. Thirdly, grounding and bonding. Grounding and bonding are essential for preventing electrical shock hazards. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of shock. Fourthly, equipment installation. Regulations cover the proper installation of electrical equipment, such as panels, disconnects, and lighting fixtures. This includes clearances, mounting methods, and environmental considerations. Fifthly, hazardous locations. Special regulations apply to electrical installations in hazardous locations, such as areas where flammable gases or dust are present. These regulations require the use of explosion-proof equipment and other measures to prevent ignition. Sixthly, lockout/tagout procedures. These procedures are designed to protect workers from electrical hazards during maintenance and repair work. They involve energizing equipment and placing locks and tags on the disconnects to prevent accidental energization. Seventhly, personal protective equipment or PPE. OSHA mandates the use of appropriate personal protective equipment, such as rubber gloves, insulated tools, and safety glasses, when working with electrical equipment. Eighthly, training. Proper training is essential for electrical safety. OSHA requires employers to provide training to employees who work with or around electrical equipment. This training should cover the hazards of electricity, safe work practices, and the use of personal protective equipment. Now let's consider how the National Electrical Code, known as NEC, plays a role in electrical safety. The NEC is a widely adopted standard for electrical installations. While it's not a federal law, it is often adopted by states and local jurisdictions. OSHA regulations often reference the NEC, and compliance with the NEC is generally considered to be a best practice for electrical safety. Article 90.3 in the NEC addresses the arrangement of the code. The NEC is divided into chapters, articles, and sections, each covering specific aspects of electrical installations. Understanding this organization is critical for navigating the code effectively. Chapter 1 of the NEC covers general requirements. This includes definitions, rules for electrical calculations, and requirements for electrical drawings. Chapter 2 deals with wiring and protection. This includes requirements for wiring methods, overcurrent protection, grounding, and bonding. Chapter 3 covers wiring methods and materials. This includes requirements for different types of cables, conduits, and other wiring materials. Chapter 4 addresses equipment for general use. This includes requirements for switches, receptacles, lighting fixtures, and appliances. Chapter 5 covers special occupancies. This includes requirements for electrical installations in hazardous locations, healthcare facilities, and other special occupancies. Chapter 6 deals with special equipment. This includes requirements for electrical installations in elevators, escalators, and other special equipment. Chapter 7 addresses special conditions. This includes requirements for electrical installations in emergency systems, standby systems, and other special conditions. Chapter 8 covers communications systems. This includes requirements for electrical installations in telephone, data, and other communications systems. Chapter 9 contains tables and examples. This includes tables for conductor ampacity, conduit fill, and other electrical calculations. Understanding key NEC articles is crucial for electrical work. NEC Article 110 covers requirements for electrical installations. This includes requirements for workmanship, equipment listing, and identification of equipment. NEC Article 210 deals with branch circuits. This includes requirements for the number of outlets on a circuit, the size of conductors, and the type of overcurrent protection. NEC Article 220 covers branch circuit, feeder, and service calculations. This includes methods for calculating the load on a circuit, feeder, or service. NEC Article 230 addresses services. This includes requirements for the service entrance conductors, the service disconnecting means, and the grounding of the service. NEC Article 250 deals with grounding and bonding. This includes requirements for the grounding electrode system, the equipment grounding conductor, and the bonding of metal parts. NEC Article 300 covers wiring methods. This includes requirements for the installation of cables, conduits, and other wiring methods. NEC Article 310 addresses conductors for general wiring. This includes requirements for the ampacity of conductors, the insulation of conductors, and the dating of conductors. NEC Article 400 deals with flexible cords and cables. This includes requirements for the types of cords and cables that can be used, the ampacity of cords and cables, and the protection of cords and cables. NEC Article 408 covers switchboards and panel boards. This includes requirements for the construction of switchboards and panel boards, the overcurrent protection of switchboards and panel boards, and the grounding of switchboards and panel boards. NEC Article 430 addresses motors, motor circuits, and controllers. This includes requirements for the overcurrent protection of motors, the disconnecting means for motors, and the control of motors. Proper conductor sizing is essential for electrical safety and is addressed in the NEC. Undersized conductors can overheat, leading to insulation damage and potential fires. The NEC provides tables that specify the allowable ampacity of conductors based on their size, insulation type, and installation conditions. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. NEC Table 310.15b16 provides ampacity values for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and installed in raceways or cables. Factors that affect conductor ampacity include the ambient temperature, the number of conductors in a raceway, and the type of insulation. The NEC requires conductors to be deaerated when they are installed in conditions that reduce their ability to dissipate heat. For example, if conductors are installed in a hot environment or are bundled together in a raceway, their ampacity must be reduced. Voltage drop is another important consideration in conductor sizing. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The NEC provides formulas for calculating voltage drop based on the conductor size, the length of the circuit, and the current flowing through the circuit. Overcurrent protection is critical for protecting electrical circuits from overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are resettable devices that trip when an overcurrent occurs. Fuses are one-time devices that melt and open the circuit when an overcurrent occurs. The NEC requires overcurrent protection devices to be sized to protect the conductors they supply. The size of the overcurrent protection device should not exceed the ampacity of the conductor. Grounding is essential for preventing electrical shock hazards. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device. The grounding electrode system connects the electrical system to the earth. This system typically consists of a ground rod, a ground plate, or a metal water pipe. The equipment grounding conductor connects the non-current carrying metal parts of equipment to the grounding electrode system. This conductor provides a path for fault current to flow back to the source. Bonding is the process of connecting all metal parts together to create a continuous electrical path. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of shock. Understanding electrical calculations is essential for designing and installing electrical systems safely and effectively. Ohm's law is a fundamental principle of electrical calculations. Ohm's law states that the voltage across a conductor is equal to the current flowing through the conductor multiplied by the resistance of the conductor. The formula for Ohm's law is volts equals amps times ohms. Power is the rate at which electrical energy is used. Power is measured in watts. The formula for power is watts equals volts times amps. The NEC provides formulas for calculating the load on a circuit, feeder, or service. These calculations are used to determine the size of the conductors and the overcurrent protection devices needed for the installation. Short circuit current calculations are used to determine the amount of current that will flow during a short circuit. This information is used to select overcurrent protection devices that can safely interrupt the fault current. Understanding transformer connections is essential for working with three-phase power systems. Transformers are used to step up or step down voltage levels. There are several types of transformer connections, including delta, Y, and open delta. The delta connection has 3 windings connected in a closed loop. The Y connection has 3 windings connected to a common neutral point. The open delta connection uses only 2 transformers to provide 3-phase power. The voltage and current relationships in 3-phase systems depend on the type of transformer connection. In a delta-connected system, the line voltage is equal to the phase voltage, and the line current is equal to the phase current times the square root of 3, which is approximately 1.732. In a Y-connected system, the line voltage is equal to the phase voltage times the square root of 3, and the line current is equal to the phase current. Understanding motor control circuits is essential for working with electric motors. Motor control circuits are used to start, stop, and control the speed of electric motors. There are several types of motor control circuits, including across-the-line starters, reduced voltage starters, and variable frequency drives, also known as VFD. Across-the-line starters connect the motor directly to the power supply. Reduced voltage starters reduce the voltage applied to the motor during starting to limit the starting current. Variable frequency drives control the speed of the motor by varying the frequency of the power supply. Safety practices are crucial when working with electrical systems. Always to energize circuits before working on them. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. Follow lockout/tagout procedures to prevent accidental energization of equipment. Maintain a safe working distance from energized equipment. Be aware of the potential hazards of electricity and take steps to minimize the risks. Always verify that a circuit is de-energized before working on it. Use a voltage tester to check for voltage at the circuit breaker or fuse end of the equipment being worked on. Never assume that a circuit is de-energized. Use insulated tools when working on electrical equipment. Insulated tools are designed to protect you from electrical shock. Inspect tools regularly for damage and replace them if necessary. Be aware of the potential for arc flash. Arc flash is a dangerous phenomenon that can occur when there is a short circuit or other electrical fault. Arc flash can cause severe burns, blindness, and even death. Wear appropriate personal protective equipment, such as arc-rated clothing and a face shield, when working on energized equipment. Follow safe work practices to minimize the risk of arc flash. Maintain a clean and organized work area. Clutter and debris can create hazards and make it difficult to work safely. Keep tools and equipment in good working order. Report any unsafe conditions to your supervisor. Ground fault circuit interrupters, commonly referred to as GFCIs, are life-saving devices designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and detect any leakage current to ground. If a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing a potentially fatal shock. The NEC requires GFCIs to be installed in certain locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. Regularly test GFCIs to ensure that they are working properly. Press the test button on the GFCI. The GFCI should trip and interrupt the circuit. If the GFCI does not trip, it should be replaced. Surge protection devices, also called SPD, protect electrical equipment from voltage surges. Voltage surges are brief spikes in voltage that can damage or destroy sensitive electronic equipment. SPD divert the surge current away from the protected equipment and safely to ground. The NEC requires SPD to be installed in certain locations, such as at the service entrance and at sensitive electronic equipment. Regularly inspect SPD to ensure that they are working properly. Look for any signs of damage, such as cracks or discoloration. Replace SPD if they are damaged or have been subjected to a surge. Remember that electrical safety is everyone's responsibility. By following safe work practices and being aware of the potential hazards of electricity, we can all help to prevent electrical accidents.